Hello and welcome. This is chapter number 8, second order circuits of our Sadiku's textbook. In this part of the lecture, we'll be talking about source-free parallel RLC circuits. So in here, we are seeing or we are given a diagram of a parallel RLC circuit. We can see that there are no dependent or independent current or voltage sources attached in the circuit. We have a resistor, we have an inductor, and we have a capacitor those are attached in a parallel combination. So the interesting question here is how this circuit powers itself up. So basically what we are assuming here is that our inductor is completely magnetized and our capacitor is completely charged at time t equals to 0, and where we basically need to see the response of this circuit. And interestingly, another thing that or another question that comes to mind is that where we see these circuits practically. So again, practically, there are certain conditions or certain situations where in our actual circuits, the system or the arrangement of inductors and capacitors is such that we are that if you want to see the response of a circuit at a particular time instant, we are left with something like this, where our inductor is having certain charge and our capacitor is having certain voltage, and we want to basically see the response of that particular combination for a future value, for a future time instant, or at a certain instant in time in future. So basically we have to find out the response for that and see how it goes. So here our first situation, or our first technique to analyze this circuit is to develop the differential equation for this circuit. And in order to develop the differential equation for the circuit, we have to solve the circuit with the help of the KCL rule. So for the KCL law, or the Kirchhoff current law, we know that the current entering and leaving in a node are equal. So here when we have to solve this circuit, we basically first apply KCL at node V. So at node, say I call this as node A because we will be using V as voltage of this node. So in order to avoid any further confusion, so I call it as node A. So at node A, what we can see is that the current is, there are three currents that are leaving and there is no current that is entering. So the current leaving are, I call it IR, I call it IC, I call it inductance L, I and IC as the conductance. There's no current entering. So we can write it IL plus IC plus IR is equal to 0. So the node at which we are measuring is at A, and the voltage at this node is given as V. So the first IR, so the IR can be written as V divided by R. Then we have IC, or the capacitor current, and we know that IC equals to C times dVC divided by dt. So we have C dV by dt. And for IL, remember we know that IL is 1 by L integral of minus infinity till t I of tau d of tau. So this is what we get, and this is basically our second order differential equation. So again, if we have to simplify it, so differentiate it. If we differentiate it, what we get is I by L plus C d2 by dt square plus 1 by R dV by dt equals to 0. We further simplify it, we get dV by dt square plus 1 by RC dV by dt plus I by LC equals to 0. So this is my differential equation, and this is the differential equation which we have to solve here in order to get to our solution. So let me call this say as equation number 1, and this is my equation number 2. So now let's solve this differential equation. Okay, so when solving this differential equation, remember that we need in the initial conditions, and the initial conditions given to us as I 0 in an inductor is given as 1 by inductor minus infinity to 0 I of back. So sorry, v of tau d tau equals to I naught, and V or voltage across the capacitor is given as V naught. This. So just putting these initial conditions in the equation 1. So equation 1, our first equation was, remember we have V by R plus C dV 0 by dt, we call it as V0, plus again 1 by L, and this basically comes out to be V naught. So if we put the initial conditions in our equation number 1, we get something like this, and just simplifying it, we get dV0 by dt equals to minus V naught by C minus V naught, minus V0 by R and C. And if we just take 1 by C common, what we are left with V naught plus V by R dV0 by dt. This is something which we are left with, or sorry, this is V naught as well. This is something we are left with, and this is a first order differential equation. And from our previous lecture, we know that if first order differential equation in similar kind have a general solution, something of a e power s of t, or we can write it as v a e power s of t. This is a general solution for a differential equation of this kind. So we use this general solution or a differential solution of differential equation, and solve our differential equation. So we use this solution, and the differential equation we developed e square, remember this one. So we use this solution to solve this differential equation, plus I by V by RC equals to 0. Remember, this is not I, this is V. So we use this equation, and we know that V is equal to a e power s of t. So using this equation and the solution, what we get is dt square a e power st plus 1 by RC, derivative of a e power st plus a e power st divided by RC. Okay. This is what we get over here. So now just simply differentiating, we get a s square e power s of t plus a s e power s of t divided by RC plus a e power s t over RC equals to 0. So we take common a e power st as common. We're left with s square plus s into 1 by RC plus 1 by RLC equals to 0. So we have, I think we forgot to add L here, and so this is sorry, V by LC, sorry. Yes, so not RC, rather LC. LC. Sorry, so we will not have any L over here. Okay, so this is what we get. So this is our differential equation. So this basically differential equation shows two things, that our A e raised to power st is equal to 0, and our second case is s square plus 1 by rc into s plus 1 by lc equals to 0. So these are the two situations which we have. So we know that this is one of the solutions to our second order differential equation. And so basically we are now more concerned about solving this this part 2, and which is a quadratic equation. We are more concerned in solving this thing. And if we are going to solve this equation, we'll get two values of s1 and s2, because any quadratic equation will have two solutions. So, and we know that solving s square plus 1 by rc into s plus 1 by lc, we know that the solutions for a quadratic equation s1 and s2 will be minus b plus minus under the root b square minus 4ac over 2a, where a is equal to 1, b is the coefficient with the second factor 1 by rc, and c is equal to 1 by lc. So remember, we this any quadratic equation can be written as a s square plus bs plus c equals to 0, and this is the generic form of any quadratic equation. That is what we use, and the solution for this sort of quadratic equation is in this form. Oh, sorry, and this is the basically solution for our different any differential quadratic equation. So with the help of this, we can see that we have s1 2 equals to minus b plus minus the root b square minus 4ac over 2a. We have a equals to 1, we have b equals to 1 by rc, we have c equals to 1 by the root, sorry, 1 by lc. So these are our three values. So now let's solve it. So b is 1 by rc, comes with a minus sign, plus minus under the root. We have 1 by rc square minus 4 into 1 into 1 by lc, with 2 into 1. So if we simplify, we get minus 1 by 2 rc plus minus, again we take 2 common from inside, so we are left with 1 by 2, sorry, 4 common from r square plus, sorry, this is a minus sign. This makes 2 outside, and that 2 is divided by 2. The 2 that is coming from the denominator. So we are left with 1 by under root LC, and we can easily take a square over here. So this thing simplifies to S1, S2 is minus 1 by 2 RC plus minus under root 1 by 2 RC whole square minus 1 by the root LC square. Okay, so this is what we are left with. So with this, we can also simplify it. We can say that alpha is 1 by 2 RC, and we have omega naught as 1 by under root f LC. So this is how we get. So we are eventually we can S1 2, or the solution can be written as minus alpha plus minus under root alpha square minus omega naught square. And this is for a parallel RLC circuit. S1 and S2 are, remember, S1, S2 are the damped natural frequencies. Omega naught is the resonant frequency of the circuit. Alpha is the damping ratio. Okay, alpha is the damping ratio. So these are the you can say values and the units, nepers per meter, and resonant frequency, resonant radians per second, and alpha is seconds minus 1. Okay, so these are the ratios for the way we are. So once we have these values for S1 and S2, so we have two values of S1 and S2, and these two values will have two specific solutions for voltage. We have even S1 of t, we'll have the second V2 A2 ES2T. So there will be two specific solutions, and those two, and the overall solution of V of t, or the voltage which we are trying to find, will be a linear combination V1 of t plus V2 of t for in this case. So this will be A1 e raised to power ES1t plus A2 e raised to power S2t with the voltage Vt. So remember, we have the initial condition for voltage V naught with us. So V naught was equal to V of 0. So we put one initial condition, we'll get one answer, and we also need V dV by dt 0 as well to find out the actual values of A1 and A2. And in a question, or whenever we are given a situation like this, these initial conditions, whether we have to find out voltage or whether we have to find out current, these initial conditions are given to us. So once these initial conditions are given to us, for first case, we will use this initial condition, develop one equation, then we'll use this initial condition, develop the other equation, and then we solve those two equations simultaneously and get the values for A1 and A2, and that values of A1 and A2 will be will give us the overall solution and overall voltage response of this circuit. So here what we have seen is that how we solve a source-free parallel RLC circuit, and how the voltage response is a linear superposition or linear combination of the two solutions which come out from by solving the second order differential equation. So in our next part, we will be solving some of the examples from this section. Thank you.